Yeah. Should take the tech from one of those headsets and put it in a spin. Cause it actually.
Sounds so easy.
Make a boundary.
Yeah, I think they're.
All right, how'd the homework go? It should be easy, right? So probably what I'm looking for the most is homework format. Like, did you create a good format? So tell me what should be in the homework format. Mine's not to format, so
Name, date, class, and time.
name, date, class, assignment is super helpful. This is not the assignment. I'm just noting that because that's your next homework set. Everyone asks, what's the next homework set? So I just put it on the paper. Right, so this should say like chapter 1, number 1 and 4 somewhere, right? And then what about the actual work? Need a good graphic, something that's not completely ugly. We're practicing our engineering skills here.
Be like a sentence saying what you're trying to solve.
Yeah, problem statement. There should be a problem statement, like, and what's the problem statement for the first one?
Cross-sectional area of a pipe.
Perfect. Maybe find the cross-sectional area of a pipe.
Or even just cross-sectional area.
Find the area. You can be that simple with me. I'm good with that. It's gonna get more complicated where you're gonna have to write a longer problem statement, but keep them short, whatever. And then what?
Little graphic.
Graphic? Not yet. There was something
Yeah,
before solution.
Given.
Huh? Given, yeah. So again, you don't have to have, like, this does it for me. Right? You don't have to have bullet points, like given is this. This is the graphic, this is what we're given, and then the solution would go down here, right? There's no problem statement, we need that. But like, you don't have to be so like bullet point type of thing. I can figure it out, just make sure it's kind of clear what's given. The given's gonna be really helpful in the future. Like, you're gonna want to extract out of the word problem, because these are all gonna be word problems, because guess what? Word problems are what we deal with in our life as engineering techs or engineers. It's a word problem that comes to you. It's not like out of a book problem, right? So you're gonna have to extract the given information out of the word problem. It's gonna get tricky. The book's really good about just giving you what you need, and I'm really bad about that because I'm gonna give you a lot more than what you need. And I want you to extract out what you need and use it, okay? Because again, in the real problem out there, you're gonna get a lot of stuff that's like unnecessary. You don't need that to solve the problem, right? So I won't give you a crazy amount, but sometimes like on a quiz, I'll give you some extra stuff and you'll be like, the hell did he give me the diameter for? I don't need that. This thing's a square pipe, right? So just use what you need kind of thing. What was given in this one?
Diameter.
Diameter and that it's a pipe, right? So those two things. All right, so what did we do? We did area equals. You can write the formula, like I tend to write the formula. And that's because I tend to share a lot of my work with other people. And if I just write the equation and answer, they never see the formula, right? And then they'll call me back and say, what did you use for inertia? Like, what formula did you use for the inertia of this, elliptical shape? And if it's there, they don't have to like call. They're like, oh yeah, use the diameter, area diameter formula. And then I put in what I have. Again, there's another formula, right? What's the other one? Pi r squared. You can use that. That doesn't matter to me. Use whatever you want. 3.04 feet squared over 4. So that's how I do it, and that's so people know what formula I'm using. If you do that, that's helpful for me, because then when you're using the wrong formula, I can see the problem. Oh, you're just using the wrong formula here, right? And we're gonna get enough formulas that you're gonna have to choose, like, oh, I'm running Bernoulli's equation. Bernoulli's equation has friction in it, has velocity, has head, has potentially another friction value, right? And it has those 4 formulas on each side of the equation with the equal sign between. Because it's called conservation of energy. Energy into the system, energy out of the system has to be equal, right? Then you can cross out some of these because we don't need them. And if you don't write that formula down, I'm like, I don't know what you crossed out, what you didn't cross out, all that kind of stuff. So it's important. All right, so what did we get?
7.26.
What's the whole number? 258, and then it probably keeps going. Yeah, okay, and that's feet squared. So then the answer for me would be 7.26 feet squared. Some kind of commitment, underline it. Good to go.
Square feet also acceptable.
Yeah, like SQFT. Yep, absolutely. That's doesn't work well if you have to reuse it in an equation. So you're gonna want to write feet squared in an equation, because then you're potentially have to, like if I said, oh, what's it in inches squared? Then you're gonna want to do that unit analysis thing and cross those units, and it's gonna look better in feet squared. Good. Questions? Super easy. Painless. All right. The number 4. What was that one? Volume of a cylinder. Did I get this right? Is the length 60 feet?
Yeah.
Yeah, it's super long. It was like 60 feet of a cylinder. It's tall. Like, how tall is that? Yeah. I mean, we could count bricks, but I'd say it's 10 feet. 60 feet. That's a lot. So when you do these problems, try to visualize what you're doing. Like, okay, we're not talking, what do they want? Cubic feet? Yeah, we're not talking 20 cubic feet here, right? We're talking some volume. All right, so how do we do that? What would the equation be?
Pi r squared times h.
Pi r squared, that's the area times the height or length. I'm gonna put L because I put L here. If you put H, use H, that's fine. Variable change is absolutely fine because you're choosing the variable. But I chose L. It's good if you identify your variable. Like if you have H in your formula, I should be able to go to your graphic and see what H is. Does that make sense? If it's not in your graphic, then I'm wondering what H is. I'm guessing it's the height, unless our cylinder is laying on its side, then it wouldn't make sense that it's the height. It'd be like the length. So, preaching here, I know. All right, so then we have pi. I'm gonna put the 130 in over 2. Like that. So there's a reasoning for that too. When I share the formula with somebody else, they want to see that I use the given information. Believe it or not, if I take 1.3 and divide it by 2 and then put it in the formula, somebody will text me and say, where'd you get the point whatever? I'm like, dude, that's half of 130. But that'll happen because people are busy and they're not thinking, they're just sending notes. And then our length is 60 feet. Yeah? What'd you get for volume?
79.64.
79.64 feet cubed. Yeah? Anybody get something different that wants to debate over it? Be a bad choice, I think. Oh, you got something different, Patrick.
Well, I don't know, like, what's the significant figures with 60 not having?
So we don't go by the book's sig fig conversation. Because it's goofy. The whole significant figure thing is goofy. The statics book says if it starts with a 1, it's this accurate. What do you mean? How can that be? Like if it's 1.78 feet and I measured it to hundreds, how could it be less accurate or more accurate than absolutely that? So we're not going with sig figs. We're gonna go just erase your little math brain, because I know you got a math brain. Get rid of that logic and just go with accuracy. How accurate is a number? We can't be more accurate to be more precise than that number. Okay. It'll take some adjustment, especially if you've been drilled on significant figures, like in a math class. Does any engineering instructor do sig figs? Like does Dryden? Gregory Mines, he might. Yeah. Interesting. Okay. Well, you gotta adjust to me. That's part of the gig, right? Is this right? Is this good?
Yep.
All right. How much weight is that? This is just an add-on. How much weight are we talking here? Did we get the weight last time of Let's say it's water. Water in the tank. How much does water weigh? We looked it up last time. 8.34 pounds per gallon. So you can probably Google weight of water in pounds per cubic foot also. That would be like one less step. The book has some, I don't know where to put it there. Not in a great spot. There's some in chapter 1. Anybody's? No, not in chapter 1. See, the book's just crappy about this kind of stuff. There's something in the back. There's some conversions. It has 1 foot equals, so in the very back, I have it tabbed. It's just sad though, as far as what they give you. But they do give you, a cubic foot is 7.48 gallons. So, I don't know, we could use that, I guess, right? If we know the weight per gallon, and if we can get from cubic feet to gallons, and then gallons to weight, since we know the weight of water. Let's do that, 7.48 gallons per cubic foot. So, 7.48 gallons per foot cubed. Why did I write it that way? Yep, so I can cross those cubic and get gallons. So now is when we don't want to use this rounded number. 79.64, we don't want to use that. We want to use the whole number because we're continuing a calculation. So that's the whole number, 79,639,3 right? 7.48 times, I'm getting 595.7.
Yeah.
Gallons. So this again is a volume, 5.595.7025, and it keeps going, gallons. And then we know we have 8.34 pounds per gallon, so we can just multiply that, the gallons will cross, we're left with pounds. 8.34 times. Oofda. But you got a number? I got 4968.
Yeah.
4968.
I did it for, cubic foot thing.
But it should come out the same, right? Weight is weight.
Well, it gave me a 62.4 pounds per cubic foot. I don't
Oh,
know if
that
that's-
should still work if the 834 is good. 4968. Anybody else get 4968? No? Oh, okay. Sorry, I wasn't looking up. Then it's 16. It's gonna round. Pounds. So now that we have that, right? We can go to our statics class and determine some forces on some legs if this thing was sitting up on legs or up on a truss. And then we can go from our statics class to our strength of materials class, and we can determine if those members are big enough to hold this weight. So we can go from fluids to statics to strengths. What a great idea. That sounds great. It's like a great like midterm exam. Thanks. All right, but that's the thing, right? We want to use our fluids to then develop some forces potentially. And then use our other skill sets to say, oh, is this good or bad? All right, questions? Questions on the homework format? That's pretty straightforward. All right. Let's turn them in. You can pass them to the left. Then I can walk down this side and get them.
What class is this?
I don't even know.
ET222.
222.
Yeah. Fluid mechanics.
That, I'm at the top of my.
I thought you meant literally what class is this? He does have a 3-week old, so we're gonna give him lots of slack with this question.
Oh, yeah. I actually slept pretty good last night.
Huh? I did, I almost emailed you and I said, oh no, don't be that way.
No, I wasn't. Doctor's appointment.
I don't know. I think I did that once. Oh my gosh. I just saw this. Like, you made a wrong answer. I talked about answer, you're like, oh, that's right.
They look good. They look good. Typically, we do our work in pencil.
Yeah.
I don't really care if you do it in pen. Some people like the pen. The problem with in pen is when you make a mistake, it's gonna either be start over or put a big X in it. That's just nasty looking, so. I prefer pencil, but again, I don't care. When things go wrong though, it's gonna be a problem to like correct it, you know, like write it up again. You weren't ready to turn it in?
No, it's not mine. I just forgot to pass it to you.
Oh, he was holding Graceland's. That would have been bad. All right. You're gonna move into chapter 1 and 2. They're both super short. Chapter 1 does talk about like metrification of the world. So, and you know, going back and forth in units, but we've done some of that already. So I don't think I need to do much with that. You'll get used to those units as we come across them. They are different, like just, you know, the primary difference that we're gonna use a lot. We're gonna use the gravitational constant. I'm just gonna use G for that. Come on, focus. So what's the gravitational constant in the metric system? Yeah, for some reason, like students know that one. And what's the unit of that? Meters per second. Squared. So that's good. That means like if we have newtons, we can multiply or divide by this gravitational constant and get mass, right? What's mass in the metric system? Kilograms or grams, right? So when you have weight, you can divide by the gravitational constant and get mass. So the next two things we're going to talk about is kind of a weight mass thing. What's the gravitational constant for the imperial system? I love that. Imperial. Or the US system. Anybody know? Isn't that weird? It's crazy that we don't know it, but we don't typically. All right, well, it's in chapter 2. And it is 32.2. It's kind of hidden in chapter 2. I can't even find chapter 2. Chapter 3. Yeah, 32.2 right here. Talks about the gravitational constant, 32.2 feet per second squared. So sometimes we talk mass, sometimes we talk pounds. So I weigh 170 pounds. Right? The way we get that, how do we get that weight? Like I weigh 170 pounds right here. On the moon, I don't weigh 170 pounds. Why? Gravity's different. Yeah. So we get it from mass times gravity. Right? So if I want to know my mass, I have to take my 170 pounds and divide by 32.2 feet per second squared. Anybody have a number for me?
5.28.
32 point, whoa, I can't. 5.27928, yeah, right? 5.2, I'm gonna write 79 pounds foot square. Weird unit, right? Anybody know what that unit is? What is mass in the US imperial system? Oregonians should know this one. Slugs. But it's not like the creepy crawly slug. It's like a bullet, a slug, right? It's a hunk of metal is what that's how it got developed into a slug. Right? A gram, I don't know if you can visualize a gram, but it's a little piece of metal also, a little chunk of metal. It's to have a little gram set up, whatever, I won't be able to find it. I'll find it though and show it to you. Right? But these are little pieces of mass. And it's how much mass your system has. So I have 5.279 slugs. The nice thing about mass is it doesn't change. Underwater, I have the same amount of mass, but gravity's different underwater, right? That's our fluid situation. Why we need mass is we need something that doesn't change when the gravity does change, right? We go to the moon, we send a bunch of mass up there. We don't send a bunch of weight. We think mass because the weight's going to change when it leaves here, goes to the moon, the weight's totally different, right? So we need the mass of things. All right, so the two properties of fluids that we're going to focus in on is density and specific weight. SPEC, specific weight. So for density, they use rho. And I'm going to make my rho like that. It's kind of a P, but if you don't put like the straight and then do the circle, then it looks more like rho. I guess you could put it a little at an angle, it might look better. So density is rho, and then specific weight is gamma, and that's my gamma, the best I can do it. Again, this is what the book's using, right? It's using this for specific weight. It's using this for density. Now, it's going to be a bit opposite of what you typically think.
How is rho spelled?
I think it's ROH, but I don't know. It's opposite of what you probably think density is. So most people out in the world think density is pound per volume, pound per cubic foot, how much it weighs per volume. That's not. That's specific weight. So the way to figure this out, and we're going to stay with the book on this, honestly, when you get in industry, this will be flipped around all the time. People will talk density in pounds per volume. People will talk density in mass per volume. It gets mixed up all the time. We're going to go with the way the book does it. I'll tell you an easy way to remember it. This says specific weight. Weight is what? What's the unit of weight? Pounds. Okay. So this is pounds per volume, or I'm going to just say cubic feet because this looks like an imperial problem. So specific weight uses weight. Density uses mass. So density is going to be mass over volume. So this would be a slug over feet cubed. The only difference between these two is the gravitational constant. That's it. The only difference. But when we talk density, we're going to talk mass per volume. Okay. When we talk specific weight, it has weight in it. That'll be pounds per cubic foot or pounds per volume. That makes sense? All right. That's the way the book does it, and that's the way we're going to do it. Just remember, when you get out there, someone's going to say, hey, the density of this thing is like, density of concrete is 450 pounds per cubic foot or something like that, right? Actually, it's 150 pounds per cubic foot. Well, you don't need to correct them and say, oh, no, it's not. It's really just, slugs per cubic foot. Like, they're not gonna want to hear that. So it does get switched around a lot. All right, good. All right, let's go back to our problem that we just worked. And I want to know how much mass is here. Okay, so we had 79.64 feet cubed. That's our volume. Right? And if we wanted mass, how much mass is in there? How much mass is in our volume of liquid?
154.3569 slugs.
How'd we get that?
Divided by 32.
It should get smaller, shouldn't it? What was your number you gave?
I did it based on the
Yeah, so if we have. Oh, yeah, you do want to base it on the pounds. Perfect. So we had what, 79.64 feet cubed. Let's work it. 79.6. I just have the rounded number. And that developed how much weight? 49. 68.16 pounds. Right? So then we would take that and divide 32.2 pounds. 32.2 feet per second squared.
We're looking for mass, right?
Mass, yep. So that,
Did weight minus, did you say weight minus gravity?
no, divided by,
Divided by.
divided by. Gotta divide it.
That was
Yep.
slightly different, but they didn't all- that's one.
Yeah, because of your start number, yeah. So what do we get for mass?
154.906.
154.2906 is the one number I got. Slugs. Yeah? Why is that important? Why would we need to know the mass of a fluid? If we were rocket scientists, we'd need to know that because that fluid's going into a different gravitational constant, right? So we need a certain amount of thrust to get it up off the earth, but then we're gonna need a lot less because there's a lot less gravity out there to move it around, right? And it's still gonna be in fluid because we need some rocket fuel up there. It's about as far as I can go with rocket science, so. Good? All right, so you have a homework set, but you also have a lab today. So you gotta do a lab write-up like we talked about on Monday. It should be a pretty easy lab write-up. Your lab is to try to determine what those four fluids are. Try to figure out what they are by calculating something. What we just covered, density and specific weight, are properties of fluids. Water has a different specific weight than, or not to get, than, than helium. Guessing there's no helium there. Right? It has a different specific weight. And you can look up these properties. You can look up the property of air. If you think you have air in one of those, you have air in one of those. Because I'm gonna let you open that one. The rest of them you cannot open. Okay? Please don't even think about opening them. And you can't even move them without two hands. You've got to move them with two hands. So there's actually a hazardous material here. So I'm gonna get big time fired if we break a jar. So, and I want everyone to experience it, right? Want everyone to experience all of them. But when you pick them up, use two hands, set it on the scale, right? Weigh it. Two hands. I'm not kidding. Two hands and set it back down. And I want everyone to do it.
Is the empty jar just?
The empty jar is so you can get measurements of the jar because we want to subtract the weight of this, right? To get just the weight of that. And to come up with a volume, you might need to do some measuring in there. It's going to be your best engineering guess at the volume, right? Because there's some curves. There might even be a taper. It's glass. So I get that. Yeah,
Can we zero the scale to the empty drum?
you can, but in your calcs, you're still gonna need it. Cause I'm gonna wanna see it.
With the weight of the drum?
Yeah. The weight of the jar.
Okay.
So, yeah, there's a term. There's also two scales, pounds and kilograms. Okay. So just be aware, somebody might hit the button and there's just a little line that's indicating above the pounds that it's on pounds, it's currently on pounds. And then there's a little line above the kilogram. Okay, questions?
Is there
So what,
something written on top of the jars?
yeah, number 1, 2, 3, and 4.
I
Yeah.
was gonna ask that.
Kind of get what you gotta do? So you're gonna come up with a weight. A weight alone is not a material property, but a weight per volume is a material property. Right? So you gotta figure out the volume that you think you have, and the levels are different in each jar, so you're gonna have to do, you know, if you don't know how to run one of these, it's got a pretty cool little depth indicator here. So you can run this up to the level of the fluid by eye. It's the best you can do. You can't open the damn lid. Don't open the lid. I want to sit right here and watch you all because somebody's going to want to open the lid. Anyway, you can kind of get the depth that way. Everything's a little rough, but. And then you're going to make your best guess as to what number 2, 3, and 4 is. Based on your calculation, not based on observation of what you think it is. If you want to do it in pairs, you can do it in pairs to collect the data, but I want everyone to experience picking all 3 up. Okay? It is now lab time. That's it. After you're done with this, then you're free to go. You don't have to write it up today, right? It's due on Monday. So your homework's due on Monday, the lab's due on Monday.
On pounds?
It is, but check on that scale. Yes.
It doesn't matter what like system we use, right?
Nope. You can use the metric system, you could use the imperial system. Is that what you meant, unit wise? Yeah, doesn't matter. Two hands. Keep it down low and those, yeah, let's not move that thing around too much.
Yeah. I know where that is.
No picking stuff up and shaking it, Brandon.
Sorry.
Damn it.
Yeah.